These cancel, and you get 7 times r equals to the ln of 1.4. Should put those in parentheses. It helps be clear what you're talking about. Finally, dividing through by 7. We get r is equal to the ln of 1.4 divided by 7. That is definitely a calculated problem. So my growth rate, by the way, is this a growth or decay problem? And so the value of r should be positive or negative. So the fact that this is positive is a good sign. Had this been negative, did something wrong. Okay. So r is equal to, well, we're going to use approximately 0.0481. Because as I said, we're going to stick to 4 decimal places in this class. The author of this worksheet, a friend of mine, by the way, uses like 8 decimal places. So when it comes to the answers here, we may be slightly off, because if you recall our conversation from last week, when it comes to exponential problems, the exponent's error, the number of decimal places you chop off, is much more significant than when you're just multiplying, because the arrow will also grow exponentially since it's in the exponent. And by chopping off, even at 4 decimal places, can create a significant difference. Just multiplying and adding and subtracting won't ever do that. But raising something to a power, all of a sudden the number of decimal places becomes much more important. So as a class, we're going to agree to do 4 decimal places using the standard rounding techniques. That means the next number determines whether this goes up or down. Since that's a 6, this goes to what? 1. That's what I've written. Okay, so we'll use those techniques. Then when we check the answers on the back page of this worksheet, just keep in mind that we're using a different value for r than he is. So our answers might be slightly off. So let's go ahead and put in what we know now. We have that the amount at any time t is going to be the initial value of 100 e to the r times t. What is r? 0.0481 times time. At this point, I can now answer a whole bunch of questions. Any time t you want, I can tell you how many aphids should be there. What is the time they asked me for? At what? After 20 days, so a of 20, oh 10, a of 10 will be equal to 100 e to the 0.0481 times 10, which will just move the decimal place over. But let's go ahead and just put it in straight because I want you guys to see how this all works out. So 100. You use your second right above the ln is the e to the x button, already set up for you. Right here above the ln is an e raised to a value all ready to go. What is that value? I'm going to write it all out. 0.0481 times 10 and hit enter. Okay.
Where'd that e come from?
Yeah, that's okay. The natural log button above it says e to the x. So I use second and hit the ln and I got my e to the x. That says to me 161.8 aphids, and since we're talking about aphids, it doesn't make sense to say 0.76 or 0.8 aphids. That's be an aphid who is somebody chopped off his head or something. No, we always round up for populations, okay? So there will be 162 aphids there. Because we're estimating anyways, better to overestimate usually than underestimate. So even if it was 161.1, we would still say that was 162 aphids. Keep that in mind when you're talking about a population. If anything over and above gets rounded up to account for the possibility of one more. Because in general, you do not want to underestimate populations. You'd rather overestimate. All right. So what did the author have to say? What was his answer? 162. Notice though on the author's definition of the function that his r value, which I think he's calling k at this point, is much longer than mine. Do you see it? It's the full version. So the next answer might be off just a hair, because now we have to figure out whether there's going to be, what, 300 aphids? Is that the next question? So that's when we take the model. Instead of putting in, I'm not looking for 300 days, right? I'm looking for 300 aphids. So that means it goes outside. 300 aphids happens when, well, at what time? So basically I'm solving this equation for t now. I need to get e all alone, so I'll divide both sides by 100 to have 3 equals e to the 0.0481 times t. Now what do I do? Take the natural log of both sides. Whenever you have e all alone, the natural thing to do is take the natural log. So you have e, 0.04181 is equal to times t, is equal to the ln of 3. Take the ln of both sides here. The ln cancels e. This comes down, and this side will be the ln of 3. And now how do I solve it for t? So t is approximately equal to what? Well, it's going to be the ln of 3 divided by this value of 0.0481. I have 22.84. I might have done something wrong. What does the author have? 22.9. Okay. If I was to take my decimal places further out here, I would probably have a more accurate example. But 22.8 versus 22.9 days, close enough in my book. We're talking about some aphids here. So I know 22 and some change days, I should get up to 300 aphids. It's all approximation anyway, so we don't need to be too concerned about the how close we are. I will say this, even the author's is still an approximation because that number that he took 9 decimal places or 8 decimal places up was even longer than that. He could have gone out 20 or 30 decimal places and been a little bit more accurate than us. So at some point we have to say enough's enough. As a class, again, I'll reiterate, we decided 4 decimal places is enough for what we're doing. Perhaps context of the problem might determine whether you want to be more accurate or not. For example, with aphids, who cares, right? A couple of bugs off, it won't really make a whole lot of difference. You start talking about the radioactive decay of, say, uranium as you're building an atomic bomb. Well, you might want to be a little bit more precise because that little extra radiation could cause you some harm. So depending on the context of the problem, how accurate you want to be would be then decided. So in the case of aphids or in most often population, 4 decimal places seems to be relatively safe. Okay. Before I go off on all of that, what can I answer about this big mess on the board now? Okay, well I want to run through this one real fast as a synopsis, just to reiterate what we've done. We took the word description that was given to us and applied this exponential growth and decay model. So that means you must memorize this model. It's not too hard. It's got 4 pieces. It's got A of t is equal to the initial amount, E raised to the growth rate times time. Memorize it. Every one of these problems uses this to start with. Doesn't tell it to you. That's your job. You pull this out, you write it down on a piece of paper. The first thing I want you looking for is the initial value. So as you scan through the problem, start looking for the initial value. In the case of the first one, it says, Kristen counts 100 aphids on 1 square foot of alfalfa. You should go up. Initial value is 100. Okay, so even have it written so you can start writing it down as you pull the information out. It's pretty hard to disguise the initial amount, but you know, English finds a way to disguise just about everything. So, you know, you can twist the words up enough. And many of you are better at that than others. So just try to find the initial amount. After that, you're going to write the initial amount in here. The next step is to find some observation. Our observation was that in the first case, that after 7 days, she counted 140. We need that observation, so we have some method to compute our value of rate of growth or decay. So we use that by plugging in 140 we knew occurred when t equals 7, and solve the equation for r. Once we have our initial value in r, we're good to go. Now I can answer a multitude of questions, whether how much after a certain number of days, or how long does it take to get to a certain number, doesn't matter. All that matters is where you put the number. If it says time, put it in for time. If it says number of things, whether it be aphids or whatever we're